Okay, today we start by going to details into the modeling procedure as I anticipated last week. So lecture of today's and of Thursday will be on the modeling procedure. In particular, today we'll discuss model conceptualization and model verification, and the other steps will be discussed on Thursday. What do we mean by model conceptualization? No problem. I do not stop on problem definition because problem definition, it is clear what it is meant by. So, for example, problem definition, I have an agricultural field. I do some agriculture, and the ditches on the side of the field, after some problem starts producing noising smells. So there's something strange going on. And this something strange may be eutrophication of the surface water body of the ditches on the side of my field. So this might be the problem definition. So let's start now to introduce the procedure of model conceptualization. Model conceptualization is meant by finding a first description or conceptual description of the mathematical model I want to implement to describe the problem I have in mind. Typically, you do model conceptualization by proposing some description of the system, typically in steady state. At least this is the beginning phase. This means I make a picture of the system and I try, picture means steady, and I try to identify the key aspect that I want to include into my model. It is again a matter of finding the right trade-off between elegant simplicity and the realistic detail. The point is, in terms of epistemology, finding the correct hierarchical level. For example, in the case I have just stated, problem definition, problem of eutrophication, I shall identify the scale, temporal and spatial scale at which I'm going to describe the phenomenon, for example, eutrophication. But in the meanwhile, I realize that I have to include some other hierarchical levels, like, for example, lower hierarchical levels. If I want to describe a phenomenon like eutrophication, I shall describe phytoplankton growth. That is one of the processes that may produce eutrophication, and this is at a lower hierarchical level in type of space. So we are going, we lower the spatial scale, but also we realize that we need to consider also higher hierarchical levels. For example, in the case of eutrophication, like the example I gave you, nutrient generation, that may, in our language, may be seen as a forcing function, nutrient load, and these pertain to a higher hierarchical level, meaning lower spatial details and higher, or if you want, lower time scales. So I identify the hierarchical level of the process of the problem I want to describe, and I shall identify also the lower and higher hierarchical levels, which are typically described in my conceptualization by submodels. In particular, the submodels on an eutrophication model may be that of nutrient generation, of a process of producing nutrients that goes into the surface water body, but at a lower hierarchical level, the process of phytoplankton growth. How do we conceptualize the description? There are several ways. First of all, we start by verbal description, as the one I introduced you in the beginning of this lecture. I have an agricultural field, and I realized that when I'm doing agriculture, the ditches of the surface water bodies receiving surface runoff from my agricultural field appear to become highly productive systems, with highly productive in terms of algal growth. And this is, for example, the first verbal description of the problem. Then typically I may employ images. I start, for example, I go to a blackboard and I start drawing the boxes, for example, identifying the state variables. State variables in this case may be, for example, nutrient loads. These are more than state variables, are forcing functions. So, and for example, I should include also chlorophyll A concentration. That is a proxy describing the process of algal growth. When I do this kind of conceptualization, as I told you, we start doing boxes. The boxes identify, for example, state variables. And when I start drawing arrows, describing interactions between state variables. And then if I want to translate this conceptualization into mathematical terms, I shall find an adequate mathematical description. Typically, in this case, we may employ arrays. As I will look at today, we will introduce adjacency matrix, but are arrays describing which state variables or forcing function are interacting with whom. And this way of describing the interaction may be also done by employing flowcharts. That is a typical way in which programmers describe the functioning of their algorithms, flowcharts, and then I may employ mathematical tools like, for example, as we will see in our laboratory lab classes, MATLAB. In MATLAB, we have a tool that is called Simulink. It is exactly a tool that allows you to introduce a description that is made up of boxes and arrows. This formalization, this way of conceptualizing a mathematical model may be done by employing several languages. In particular, traditionally, in ecology, we employ this kind of diagrams. These are energy flow or energetic schemes in which, for example, we try to describe the fact that some energy producing processes, like the process of algal growth, are fostered or are fueled by energy inputs that may come from nutrients. These nutrients may give rise to biological processes, like it is, for example, nitrogen or phosphorus consumption. And this has as an output production of phytoplankton. And this production of phytoplankton may be controlled by external factors like forcing function, like maybe the temperature or physical-chemical characteristics, like, for example, the viscosity of the water or temperature of the water and so on. At this point, when we may employ electronic charts, we are implicitly including some mathematical meaning into the symbols that I'm employing. In this case, for example, mathematical meaning may be given by this kind of boxes in which I have nutrients and phosphorus concentration. So as nutrient grows, I may see, or I may make a big hypothesis that I have a growing chlorophyll A concentration, describing the fact that I have algae growing. The important aspect of this way of conceptualizing the problem is that I may include already some information concerning the hierarchy of the processes, like in this diagram, and I start identifying at this point what we have called the currency of a model. So what we have called, what we are using to describe, for example, interactions in terms of, for example, phosphorus or nitrogen flows or chlorophyll A's and so on. Typically, I may employ energy currencies to describe ecological or economic processes, but as we have already introduced, we may switch from energetic description to mass description. This is due to the fact that, for example, when we deal with biochemical processes or when we deal when we have to do with, for example, biomass, there are some general principles like the fixed stoichiometry principle that allows us to switch easily from energetic to mass descriptions. Just to make explicit what we are meaning here, I'm proposing here a first conceptual diagram. The typical way of, for example, describing a lake eutrophication problem. This is a model describing lakes. In this case, the currency is phosphorus. So we look at the dissolved phosphorus, phosphorus in algae, phosphorus in detritus, phosphorus in herbivorous fish, and so on. Each boxes correspond to a state variable, and arrows corresponds to processes linking the different state variables. For example, the phosphorus in herbivorous fish is linked to the phosphorus content in carnivorous fish due to the fact that carnivorous fish feed on to herbivorous fish, so there is a transfer of a material from the herbivorous parts onto the carnivorous parts, onto the carnivorous species. Another important aspect we shall consider is that when I'm doing this kind of conceptualization, I may also introduce some kind of differentiation due to different parts of the system. In particular, in this case, and I recall you that we are talking about a eutrophication model with a phosphorus currency, we may subdivide or divide my system into the epilimnium, the part of a lake that is above the thermocline, the hypolimnium, the part of the lake that is below the thermocline, and the sediment in this case. So we may introduce also flows, arrows describing exchanges between, for example, detritus into the epilimnium and detritus into the hypolimnium. In particular, these arrows describe the process of sedimentation. Sedimentation is the transfer of material from the epilimnium to the hypolimnium. Again, for example, let's look at the arrow number 13. If you go and look at 13, 13 is settling of algae. So in this case, these are transfers of algal cell from the epilimnium, crossing the thermocline and going to the hypolimnium. For example, if you look at process number 16, this is the detritus phosphorus. Process number 16 is settling of detritus hypolimnium sediment, so passing of detritus from the hypolimnium to the sediment. Then I may be quite detailed in this kind of listing of processes. For example, I may also include processes like let's say like process 14, that is exchange of phosphorus in setting up the tricycle, setting polymorph, this is, sorry, 14. Exchanges of phosphorus from the phosphorus fraction contained into algae into phosphorus contained into interstitial waters. So these are exchanges that move material from the different parts of the system, the ecosystems I'm modeling. I recall you that I'm focusing here on a lake model. The interesting part here is that we use a very general approach for describing the processes. That is the conceptual model made up of compartments and flows. I recall you that compartments generally represent state variables, while flows represent interactions between the state variables. So we describe our system by assumption as a network of flows between compartments. This description, that is, might be arbitrarily detailed, is made up, for example, by identifying state variables. In this case, 1, 2, 3, the boxes identify state variables, and then interaction between various state variables that are two-way interaction. For example, we may write interaction between state variable 1 and state variable 3 by describing the flow J31, that is the flow of exchanges of material between state variable 1 and state variable 3. Exchanges of what material? The material is the currency we are employing for describing my model. In the case of this eutrophication lake model, I'm using as currency phosphorus. What is the advantage of doing or employing this kind of schematization? The first advantage is that I may conceptualize quite an arbitrary, complicated description by introducing a number of state variables and a number of interaction between the state variables. And by describing the system this way, I may immediately obtain some indicators that are, for example, holistic indicators of the behavior of the system. In this case, we may, for example, calculate the total system throughput, that is the sum of all the flows. I call you that these are oriented flows, so J31 is different from J13. J31 is the flow of material from state variable 3 to state variable 1, while J13 is the flow of material from state variable 1 to state variable 3. I make all the summation and I obtain a first indicator of the performing of a network. That is, for example, the total system throughput. That is a kind of measures of how much the system is working in terms of exchanges of material. The total system throughput is somehow analogous to the temperature of bodies, so it is an holistic indicator, an holistic descriptor of the system, by which we concentrate, we cluster all together a series of processes that may be even quite complex. We give up the pretension, we do not pretend to describe all the details. Instead, we are looking, or we are seeking for holistic indicators that can give us some information concerning the performance of the system. As I told you, temperature is a good example of an holistic indicator. For example, for mammals, we all know that if a temperature, in particular for mammals with the two legs, like for example humans, the temperature, the holistic indicator temperature has a threshold value that is 36 degrees. And if we employ a temperature indicator, we know that if the temperature is higher than 36 degrees, then we have an indication that something wrong is going on with the physiology of his organism. So fever is an example of an holistic indicator describing the performance of a complex network of interactions between several state variables and several processes of interaction of the state variables, producing a kind of holistic description that allows us to find some kind of information concerning the performance of the system. You may imagine that this way of conceptualizing ecological model is too simplistic, but this is not the case. I give you this example. This is the Palude della Rosa network, trophic network arrows. The Palude della Rosa is a portion of the Lagoon of Venice, in which we have interaction between several elements. In this case, this is a model, and we will see some of these models when we will discuss trophic network modeling. This is a mean annual model referred to the years 2001, in which we have measured the quantity of different biological elements. For example, the state variable here are carnivorous fish, globules of Icephalus, or omnivorous fishes, and so on. And we link all these state variables by arrows of interaction. For example, the globules of Icephalus feeds on macrobentonic predators or on Carcinus mediterraneum, Carcinus del granchio. And by making this description, we may also include a lot of information concerning, for example, the size of these boxes are proportional to a biomass. So the larger the box is, the more of this state variable is present in my system. And the displacement along the vertical of these boxes give also information on the trophic levels of the various organisms participating to the trophic network. In particular, we start by the lowest trophic levels, that are that of phytoplankton or planktonic detritus or benthic detritus, and then we go progressively to high trophic levels. For example, these microzooplankton, Lysa spinosum, these are fishes, macrobenthic suspended feeders, macrobenthic detritivorous fishes, and so on. And these are trophic level, but it is around the second, more or less. As we will see, we may have fractional values of trophic levels. So, for example, if we have a boxes around here, these trophic levels shall be contained in the interval 1, 2. Then we may go up with the trophic levels, going up to the highest trophic levels. In this case, we have carnivorous fishes, but we may also go upper, and we may include also birds or even the humans that are fishing, for example, into the system and are acting as an particularly relevant flow of material from the lower trophic levels to higher trophic levels, that, for example, that of fishery productions. Okay, so the conceptualization by arrow and boxes is a very general description that is applicable to several dynamic processes. By employing a description by boxes and flow, we may describe all or almost all dynamic processes. Again, when we start doing the conceptualization of a complex ecological system, we are faced with the problem of defining somehow the complexity of the system. We realize and we recognize now that nature is complex. For example, it is not possible to describe the reaction of all species in all possible combinations for forcing. So there is a kind of uncertainty principle. So this uncertainty principle tells us that not all components or processes of an ecological system can be described all at once with an arbitrary accuracy. So I have to give up pretend to describe all the details with an arbitrary accuracy. Instead, we reduce the number of details and we reduce also the accuracy by which we describe these details. We may formalize this uncertainty principle by borrowing the concepts from physics. For example, we may say that the product of a number of elements of a model, for example, the number of state variables, and the descriptive accuracy of a model may have an upper limit. We may write this by saying that we try to find a compromise between describing all of nothing and nothing of all. So the idea is that we may formalize this numerically by writing that reverse of the product of a number of elements of a model times the uncertainty by which we describe these elements as a lower limit, and this represents the uncertainty of our description. This means, written by this means that if the number of elements increase, then I will have to reduce the accuracy of my description. If you think at the Heisenberg principle, which, for example, it was stated that we cannot describe simultaneously with the same accuracy the position and the speed of a particle, you see that the parallel is quite striking. It is quite evident. So we are faced with the problem of evaluating the complexity of a system or of a model I employ to describe this system. So we have now to define complexity. And when we start asking ourselves how to measure and to define complexity, we are at the conceptualization stage of my model. So conceptualizing a model means also defining, besides the hierarchical level of my description, also defining the complexity of my description. And theoretically or hypothetically, the complexity of my description should be consistent with the complexity of the system I want to describe. So the more complex the system, the more complex the description I shall employ. So we start by recognizing that ecological systems are generally complex. Conceptual models, now you understand, can be made arbitrarily complex. For example, in the box and arrow schematization, we may include increase the number of boxes and increase the number of interaction or the number of arrows between the boxes. In general, we know that mathematical models are simplification of a system, so in a way we may say caricatures. This means that we try to emphasize the aspects of the system we are interested on, by which or for which our description shall be focused on. The degree of simplification of the system or the model complexity is determined by the availability of data and is limited by our knowledge of the process. So there are some more limitation that allows us to define, for example, the K with uncertainty principle, so the limit of our knowledge. These limitations are due to the quantity of knowledge concerning our system, which is the availability of experimental data, and by the knowledge of the processes that are undergoing or by which these data are interacting. Then the iterative process of simplification is conducted first on the conceptual model. Why it is important to start with a conceptual model? Because we define the hierarchical level of our description. We define the submodel in terms of lower and upper hierarchical level. But In the meanwhile, we also define the scales of our description. So, for example, we have indication of what kind of experimental observation we need to do in order to obtain a set of experimental data that are relevant for the calibration of a model. The iterative process of simplification is when conducted on the conceptual model. The conceptual model displays a certain level of complexity. The level of complexity of the conceptual model should be consistent with the complexity of the system you want to describe. There is a conceptual definition of a base model that was produced by Ziegler in 1976. The base model considers all the input-output relations. In general, we recognize that this kind of model is simply too complex. It cannot be mathematically treated, and sometimes it is even not manageable even by computers, because, for example, if my model is so complex but in order to solve equations, for example, describing 1 month or 1 season of a system evolution, I need to make a calculation that takes, for example, 2 years of CPU times calculation, then my model is useless, is not useful at all. If I need, for example, 10 times the time for calculating the resolution of the differential equations describing the interaction of my ecological systems, then my model is useless, because the forecasts, the provisions provided by the model are simply too cumbersome from the computational point of view. In order to be more precise, now we start describing a way of evaluating model complexity. In order to do so, we shall present a set of different models. For example, we focus on a particular ecosystem, and we decide that this ecosystem may be described by 12 variables. For example, suspended solid, water, fish, benthos, pore waters, and so on. These are simply descriptors of the status of my system, and I start listing or drawing by conceptualization of the interaction between the state variables by boxes and arrow scheme, writing arrows connecting the various state variables. So here we have T1, T2, T3, T4, T5, and T6, 6 possible different combinations of boxes and arrows into my model. By these 6 different ways of combining, we may introduce a description by an adjacency matrix that drives us to the definition of model complexity. The adjacency matrix, for example, is a matrix in which we put 0 if there is no interaction, and 1 if there is interaction between the state variables. For example, in the case of this 12 state variables model T1, T2, T3, T5, T6, we will produce an adjacency matrix that is typically a matrix like this one, in which we have the state variables, number of state variables on the arrow, and the state variable, on the horizontal line, so on the rows, and the state variables on the columns. And we put 1 if there is an interaction, so if there is a flow connecting the state variable, and the 0 if there is no interaction. This matrix, that is the base matrix for starting the evaluation of complexity of a model, is called the adjacency matrix. In particular, this matrix is matrix describing model T4. T1, T2, T3, T4, so this model up here. For model T4, for example, we have an interaction between state variable 11 and the state variable 3. So you look 11 and sorry, if you look 11 and state variable 3 here, we have a 1. So there is an interaction that goes from 11 to 3, but there is also an interaction that goes from 3 to 12. In this case, 3 to 12, we have a 1 here. So this kind of representation, it is the first way of representing the topological condition of a model in terms of who is interacting with whom. So this is a tentative way of describing how much the traffic network model is connected. So how much my model of interaction and flow in box model is connecting. The more the flows, the more the connectivity. In order to evaluate this connectivity, we may introduce the direct connectivity index. You may recall it is as the total system throughput. We have seen some slides before. You may recall that the total system throughput is an holistic indicator of the performance of the model, the box and flow model. Again, here the direct connectivity indicator is an indicator that tells us how much the model is directly connected. Please note that we have decided to put arbitrarily 1 if there is any kind of connection and 0 if there is no connection at all. The interesting part of this way of describing interaction between the elements of a model, this is, for example, the adjacency matrix model, so the adjacency matrix for model M4. This is another way of representing conceptually by our own flows in our model. Again, here we have 8 state variables. Please note that I'm voluntarily confusing forcing and state because these are all variables that maybe refer to the external environment or to the internal environment. So, for example, 8, it is an external variable describing environment, the external environment, while, for example, 7, the input is an external variable describing a forcing aspects of forcing effects coming from external into the model. So, for example, for model 1, 2, 3, and 4, so for this model and 4, this is the adjacency matrix. So we are translating this conceptualization in terms of arrows and boxes into a first matricial description, and the direct connectivity index is trivially calculated by summing the number of ones into the matrix and divided by the potential total number of ones, that is the square of n. So if these were all, when everything is connected to everything, we will have an n square connection, direct connectivity. So we are normalizing the number of ones by the totality of possible ones that may appear in our description. These ways of evaluating or treating the conceptual model in terms of arrows and boxes bring us to the definition of a more sophisticated index, the so-called Bosserman index, that is an indicator of recycling. How do we calculate this index? We simply make the powers of the adjacency matrix. So we start from the adjacency matrix A, that if I'm not wrong is, check. We start, yes. This is the model T4 adjacency matrix. Yes, and if we make the power in the algebra of matrices of the adjacency matrix, we obtain matrix A square. we make the first exponent, so cube matrix A3, matrix A4, and so on. What are we doing here? We are simply counting how many connections of two jumps, for example, while the adjacency matrix counts how many connections of one step links the different state variables, the square of the adjacency matrix counts how many connection of two steps connect to different state variables. The same with the cube. The cube counts how many connection of three steps, three jumps connect with different adjacency matrix. Of course, the smart student recognizes that if I'm making the square of the adjacency matrix A, I will not only have ones and zeros, but I will have zeros if no connection, and a number telling me how many connection of length n, in particular here of length 2, are present connecting to state variable. So the assumption here is that I put 0 if 0, and I put ones if I have a number different from 0. This means that in the square of the adjacency matrix, I will have ones if there is at least one step of length 2 connecting the two state variables. This way, I am evaluating how much the currency is flowing into the network. So this is a topological analysis of the connectivity of a network. And by making this kind of analysis, I may produce a much more sophisticated index, that is the Bosmer recycling index, that is made up by summing all the ones in the adjacency matrix, the square of the adjacency matrix going up to nth power of the adjacency matrix, divided by nth to the cube. This index, what is called Bosman index, is another holistic indicator giving us an idea not only of the topological connectivity of our network, who is connected by whom, but also giving some indications on how much the currency is circulating or cycling inside into the ecosystem. You may recall that when we introduced the definition of ecosystem, we said that internal recycling of nutrients is a key aspect that cannot be neglected, because the relevant aspect is that the nutrients, for example, are not destroyed, instead are transformed or moved from one part of the ecosystem to the other. This is a way of measuring how much nutrients are cycling. So how do we employ the direct connectivity or the Bosman cycling index in order to evaluate the complexity of a model? If we make a table for these indexes computed for the model M1 to M6 and T1 to T6 as presented before, we may have different values of these indicators. In particular, we distinguish between no internal recycling, so the AJJ equal to 0. That means that there is no internal recycling to the box and arrows description, or AJ1, so the internal recycling is total. So everything that is produced by one state variable goes back to the state variable itself. By making this kind of approximation, we may calculate the two indicators, in particular the first column here represents direct connectivity, while the second column here represents the Bosman recycling index. How do we employ these indexes in order to define the complexity of a model? We look at how much these indexes changes. For example, let's focus our attention on the model M's, and we look model M's with total internal recycling, and we look at the Bosman recycling index. we realize immediately that there is a gigantic change, or a very relevant change of the recycling index between model M1 and model M2. Between model M1 and model M2, we have a significant changes of the recycling index. This means that if we increase the complexity of our model passing from M1 to M2, we are increasing the complexity of our description in a significant way, so that indicators, holistic indicators like the Bosman recycling index are significantly changing. Then between model M2 and model M3, we are almost constant. We have a second step of increase between model M3 and model M4. We pass from 0.69 to 0.72. And then we have a final important increase between model M5 to model M6. How do we employ this number? We employ this number by simply saying that passing from model M1 to model M2 is relevant, meaning that we are significantly changing the complexity of our model so that the complexity of response is changed as well. And we may say that, for example, passing from model M3 and model M4 to model M5, it is not so significant. So we are increasing the complexity of the model without obtaining a significantly different response concerning the description of my system. So this is the first guidance. The Bosman recycling index is the first guidance that allows us to define the complexity of my descriptions and allows us to find the most suitable level of complexity I need to implement in order to have a significant description of the system. So the comparisons between the indices of direct connectivity and Bosman's for the various models proposed or for the same ecosystem is the way of defining the model complexity and to verify that the model complexity is consistent with the complexity of the system I want to describe. There are other ways of measuring the complexity of a model. The other very significant one is that of employing the buffer capacity. Buffer capacity, as we will see, is the reverse of the ratio between a variation of a state function st as a consequence, for example, of a variation of a forcing function. In this case, if we plot forcing function against state variables, we see that passing from this level of forcing function to this level of a forcing function, sorry, I need a pen. Here, here we do not have a significant variation of the state variable as a consequence of a significant variation of the forcing function. Again, here we do not have a significant variation of the state variable as a consequence of a significant variation of the state function. Instead, here we have significant variation. So when the derivatives, if you want, of the value of the state function on the variation of the forcing function, if this value is large, then the system appears to be extremely sensitive, and so the adding of the new state variable st may increase our knowledge concerning the system. Of course, we have several buffer capacities, have a combination between state variables and forcing functions. It will be the purpose of the model that indicates which buffer capacity to choose. For example, in the case of a eutrophication model, I will be very interested of employing phosphorus loss, for example, the lake model in which the currency was phosphorus, and for example, the concentration of phytoplankton as measured, for example, as chlorophyll A concentration. So, so that we may say that in this interval of variations of the forcing function, we do not have a significant variation of the state variable. Instead, in this interval of variation of the forcing function, we may have a significant variation of the forcing function of the state variable, sorry. I'm looking if I have the opportunity. So this is the point, the interval in which the small variation of forcing function may generate dramatic variation of the state variable. We have a similar type of analysis. For example, if we plot the state variable, sorry, the buffer capacity as function of the state variable, you may recognize that if you increase the number of state variables, you are increasing the complexity of a model. So if I look at this type of graph, this tells us that increasing the state variable up to point, let's say up to here, has a meaning, while once I have reached this level, the new increased number of state variables added are not changing significantly the buffer capacity. So this is a useless increase of the complexity of my description, but does not help me in describing the complexity of my system. Is it clear? Do you have any questions concerning this? No, okay. Let's then go on, continue. Let's pass to the step of the verification of a model. That is a trivial, simple study, but allows us to verify or to be sure that the model performs as I expected him to perform. A model is said to be verified if it behaves in the way in which the model wants it to be. Trivially, for example, if we have dissolved oxygen as a state variable, and if we have temperature as a forcing function, if I increase the temperature, I expect that the dissolved oxygen concentration decrease. If this is not happening, then there is something wrong from the point of view of inclusion of my understanding of the processes into the system. So during the verification step, it is a kind of a pre-analysis of the behavior of a model that tries to allow us to be sure that we are including all the details that are considered to be relevant for my description. In order for a model to be verified, first of all, we have to be sure that the model exists, so that there are equations linking state variables. We have to find some reasonable values of the parameters. For example, one parameter may be the settling velocity of phytoplankton, or one parameter may be the growth rate of zooplankton. So we shall be sure that these parameters that I recall you become calibration knobs or calibration aspects of my models, and displays reasonable values. Reasonable, we will see later, means values that may be found in literature from the analysis of real systems. And then we need to have experimental data on the system are needed to verify that the model is exactly behaving as the model expects it to behave. There are several other types of checks that the model may want to do in order to verify the behavior of a model. For example, the first check typically is that the control of error is the errors are not mutually correlated or not correlated with the input. This means that if I make the difference between simulated and observed data, I'm expecting that on the average, the difference shall be 0. So this means that my models, let's say that we have some experimental data points. I would like to change the colors of this door. I'm not able to do that yet, but this means if the output of the model is something like this one, you may see that on the average, the results of my model are have a 0 difference from simulated and modeled data or observed data. Then you have to check the internal logic of the model, as I told you, for example, if I have an increased load of BOD5, I want to be sure that I will have a decreased concentration of dissolved oxygen. Or, for example, as I told you before, if I have an increase in temperature for same function, I expect a decrease in dissolved oxygen concentration. Or if I have increase in nutrients, increases in chlorophyll A, so this has to do with internal logic, inclusion of the relevant processes and the effect of the relevant processes. And then the last point you should check is to verify the internal stability of the model. In order to verify internal stability of a model, the long-term stability of the model, I shall check that I do not observe behaviors in which I have, for example, an oscillation of values and then running away of the state variable. What is an explosive deviation or derivation of the value of the state variable. Instead, I am more happy if the state variable maybe oscillates, but around kind of, there is a transient value of the state variables tends to go back to a stable performance of a model. So these are all checks that the model shall be ready to do in order to verify that this description is performing in a consistent way. Okay, I think we shall stop here today. Do you have any questions? We don't have any questions, so we shall check. I stay in the class for some minutes, and then I close the class and we go next.